Welcome to the next session on support vector machines. In part 1 of SVM, we had an introductory discussion regarding support vector machines. We talked about the data that is linearly separable and linearly non-separable. We had seen one example and tried to briefly understand the maximum margin classifier, and finally we had a discussion about what are support vectors. To continue our discussion further, let us once again look at the example in two-dimensional space. We have the positive samples and the negative samples. Those are described by two features, x1 and x2, and these observations or the samples are depicted here. As we have seen earlier, this data set is linearly separable, and if we want to classify these samples into two target classes, positive and negative, it is possible to have the linear hyperplane that can segregate the data. Also, as we have seen, we may have number of hypotheses or many number of hyperplanes. Those can be used to distinguish the data, but we are interested in selecting or choosing a hyperplane or a decision boundary that actually maximizes the margin between the support vectors. You can visualize the concept in this figure towards right. So, the main task of SVM is to find the best separating hyperplane or decision boundary for the training data set that maximizes the margin. And what is the reason why we would like to maximize the margin? If we are having the smaller margin, it means there are more chances for the points to get misclassified. If we keep the margin as wide as possible, we are reducing the chances of positive and negative points to get misclassified, and that is the reason why we are emphasizing on maximizing the margin. Now, let us talk about the intuitions about margins and about the confidence of our predictions. So once again, let us refer to the concept of logistic regression that we have studied earlier. We have already discussed about this logistic regression algorithm, which is a machine learning algorithm for classification. The hypothesis of logistic regression h theta x actually gives us the probability that the sample is having class 1 given x parameterized by theta. I'll repeat, this hypothesis is actually giving us the probability that the sample is of the class y equal to 1. Say for example, if h theta x is evaluated as say 0.7, this means that the probability that the sample is of class y equal to 1 is 0.7 or 70%. So obviously the probability that the sample belongs to class y equal to 0 is 0.3 or 30%. In fact, in logistic regression, the hypothesis h theta x takes the form of a sigmoid function or a logistic function. This h theta x is denoted as g of theta transpose x, where this g of theta transpose x is a sigmoid function and it is given as 1 divided by 1 plus e to the power minus theta transpose x. Now please look at this figure, how we can draw the sigmoid function. So this red color plot is actually showing us the sigmoid function, or it is also called as the logistic function. Now for simplicity, let us assume that this theta transpose x is z and our hypothesis h theta x is denoted as g of z, and this red plot denotes my hypothesis h theta x or g of z. So here on horizontal axis we are having z, that is theta transpose x, and on the vertical axis we are having our hypothesis h theta x or g of z. So this plot actually is giving me the value 0.5. So my hypothesis is equal to 0.5 when my z is 0. So g of 0 is 0.5. As I go on increasing the value of z, what will happen? My hypothesis value will also increase till 1. Whereas if I go on decreasing the value of z, my hypothesis h theta x will go on decreasing. And obviously it is the property of the sigmoid function that the hypothesis value is between 0 and 1. So for different values of z, I am getting the value of my hypothesis g of z within the limit 0 and 1. So once again look at the figure. It has been shown here that we are going to predict our sample, input sample x as 1 if and only if hypothesis h theta x is evaluated as greater than or equal to 0.5, or equivalently we may say that we are predicting the input sample x as 1 if and only if our z is greater than or equal to 0. That means if theta transpose x is greater than or equal to 0, we predict the input sample x as 1. Let us consider that we have a positive training example. That means we are having a training example with y equal to 1. The larger theta transpose x value means we are having the larger value for h theta x. That means we are having the higher probability that y is equal to 1 given x. That means if h theta x is high, the degree of confidence that the label is 1 is also high. Or to summarize the things, we may say that to predict the label as y equal to 1, we want our hypothesis h theta x as nearer to 1, or in other words, we expect theta transpose x is much greater than 0. On the contrary, if we are labeling the sample as y equal to 0, this means that our h theta x is near to 0 or our theta transpose x is very much smaller than 0. Thus, informally, we can think of our prediction as being a very confident one, that is y equal to 1 if theta transpose x is greater or very much greater than 0, and similarly we think of logistic regression as making a very confident prediction of y equal to 0 if theta transpose x is very much smaller than 0. Now, for a different type of intuition, let us consider the figure that is shown on this slide. Here we are having positive and negative training examples and a decision boundary. This decision boundary is of the form theta transpose x equal to 0, and it is also called as the separating hyperplane. This hyperplane is classifying the positive and negative samples. So, class for positive samples is y equal to 1 and class for negative samples is y equal to 0. Now, look at these 3 points labeled here as A, B and C. These 3 green dots, A, B and C. If we consider this point A, this point is very far from the decision boundary. If we are asked to make a prediction for the value of y at A, it seems we should be quite confident that y equal to 1 at this point. That means we can label this point A as y equal to 1 with very high confidence. Why? Because A is far from the decision boundary. And now conversely, look at this data point C. This data point C is very close to the decision boundary, and while it's on the side of the decision boundary on which we would predict y equal to 1, it seems likely that just a small shift or a small change to the decision boundary could easily have caused our prediction to be y equal to 0. So, we may say that data point C is labeled as y equal to 1 with very low confidence, and the reason is C is very close to the decision boundary, and a small change in the decision boundary may change this result for data point C. So, low confidence. Hence, we are much more confident about our prediction at A than at C. The point B lies in between these two cases, A and C. And more broadly, we see that if a point is far from the separating hyperplane, then we may be significantly more confident in our predictions. So obviously, it would be great if, given a training data set, we could manage to find a decision boundary that allows us to make all correct and confident predictions on the training examples. And that is what we are going to discuss next, how we can do that. Now, we are going to formally discuss two important kinds of margins known as functional margin and geometric margin. To make our discussion of SVM easier, I would like to introduce a new notation for talking about classification. We will be considering a linear classifier for binary classification problem. That means we are considering a linear classifier to classify between two classes. So we have two target classes. Let us assume that each instance in the training set is denoted by x comma y, where x is a feature vector describing an instance and y is associated label or a class. We are talking about binary classification, and hence our set y has two values or two class labels, -1 and +1. So y belongs to -1 and 1. As per our earlier notations, we said that our hypothesis is denoted as h theta x equal to g of theta transpose x. This was our earlier notation. Now we are changing our notations as our classifier hypothesis now will be written as HWBX is equal to G of W transpose X plus B. So earlier we had the parameter vector theta, and now we are parameterizing our hypothesis with parameters W and B. So our classifier hypothesis is HW comma BX equal to G of W transpose X plus B. Here G of Z is equal to 1 if Z is greater than or equal to 0. Otherwise, G of Z is equal to -1. This W and B notations allow us to explicitly treat the intercept term B separately from the other parameters. So let us recall back our earlier notations and try to relate old ones with the new notations. So here B is equivalent to theta 0 according to our old notations, and W takes the role of the vector theta 1, theta 2 up to theta m. Also note that according to our new definition of classifier hypothesis, the function g will directly predict either 1 or -1 without first computing or estimating the probability of y being 1. That is what we did in case of logistic regression. So I hope you must have understood and noticed the difference in our earlier notation and now this new notation. Now let us try to formulate the notions of the functional and geometric margins. Let us see now the same figure that we have seen earlier. So we are having few samples, those are positive and negative. Those are described with two features x1 and x2. We are having the hypothesis. The hypothesis or the hyperplane or the decision boundary is represented as W transpose X plus B equal to 0. This is a linear form of our hyperplane. Here W is a vector and X is also a vector. we are having two features x1 and x2, our hyperplane can be represented as w1x1 plus w2x2 plus b equal to 0. So, this hyperplane is classifying or distinguishing our positive samples from the negative samples. So, we are having towards one side of the hyperplane class y equal to 1 and towards another side of the hyperplane class y equal to minus 1. Now, with this background, let us try to define functional margin. Given training example xi, yi, the functional margin of w comma b with respect to the training example is given as gamma I hat equal to yi into w transpose x plus b. I will repeat, gamma I hat equal to yi into w transpose x plus b. Note that if yi is equal to 1, then for the functional margin to be large, that means for our prediction to be confident and correct, we need w transpose x plus b to be a large positive number. So, if yi is equal to 1, then for the functional margin to be large, w transpose x plus b should be a large positive number. Conversely, if yi is equal to minus 1, then for the functional margin to be large, we need w transpose x plus b to be a large negative number. I repeat, if yi is equal to minus 1, then for the functional margin to be large, we need w transpose x plus b to be a large negative number. So, in essence, a large functional margin represents a confident and a correct prediction. Now, let us extend our discussion regarding functional margin that we are going to use later whenever we will go for the optimization problem. So, once again we are dealing with the same binary classification problem. We are having positive and negative samples and the decision boundary or the hyperplane denoted as w transpose x plus b equal to 0, and this plane is classifying the samples in two classes, y equal to 1 and y equal to minus 1. So, let us once again write our classifier hypothesis parameterized by w and b. So, h w b x is equal to g of w transpose x plus b, and we said that if this w transpose x plus b is giving us a large positive number, then the class of sample xi, that is yi equal to 1, and if w transpose x plus b is giving us a large negative number, then the class of the sample yi would be equal to minus 1. Actually, we are choosing our hypothesis G, that is having the parameters w and b. So, while selecting this hypothesis G, what if we replace our w with 2w and b with 2b? Let me explain this with one example. Suppose our decision boundary for a given problem is given as 2x1 plus 3x2 plus 5 equal to 0. Correct? It takes the form w1x1 plus w2x2 plus b equal to 0. Now, instead of having this linear function, if I take the function g, which is a linear function for a line or for a linear decision boundary, as 4x1 plus 6x2 plus 10 equal to 0. So earlier I denoted my boundary as 2x1 plus 3x2 plus 5 equal to 0, and now my decision boundary is of the form 4x1 plus 6x2 plus 10 equal to 0. So whether these two functions are same or not. Obviously, these two expressions or these two linear functions denote the same line even though the parameters w and b are different. In second case, we have scaled our w and b by 2. So, these two functions are giving me the same hypothesis or the same line with different parameters w and b. In fact, the parameters w and b are been scaled. Here, what we have observed is g of w transpose x plus b is equal to g of 2 w transpose x plus 2b. This indicates that there is no change in hypothesis hwbx if we scale the parameters w and b. This implies a very important point. The hypothesis hwbx depends only on the sign of w transpose x plus b, but do not depend on the magnitude of w transpose x plus b. So, I will repeat, the hypothesis hwbx depends only on the sign of w transpose x plus b, but do not depend upon the magnitude of w transpose x plus b. However, replacing wb with 2w 2b results in multiplying functional margin by a factor of 2. That is, if I am scaling the parameters w and b by 2, then my functional margin will also be scaled by 2. Thus, it seems that by exploiting our freedom to scale w and b, we can make the functional margin arbitrarily large without really changing anything that is meaningful, and hence it makes sense to impose some kind of normalization condition such that norm of w equal to 1. That is, we may replace w comma b with w divided by norm w comma b divided by norm w. And now we may consider the functional margin of w by norm w comma b by norm of w. We'll come back to this concept later whenever we'll be using this while formulating the problem. Now we have seen how to define functional margin for a single sample in the training set, and now we are going to define functional margin for a given set of training examples. So let us assume that we are provided with a training data set S with n number of samples. So S denotes a training data set having the samples xi, yi, and I varies from 1 to n. And now we are supposed to find out the functional margin of w comma b with respect to this entire set S. So what we will be doing is, we will be finding out the functional margin of every data point belonging to S. That means for every xi, yi, we are going to compute gamma I hat, and out of these n functional margin values for n samples, we will be finding out the minimum value of functional margin, and that would be the functional margin of a training set S, and it is denoted as gamma hat. Thus, the functional margin of w comma b with respect to training set S is defined as the smallest of the functional margins of the individual training examples, and this is denoted as gamma hat is equal to minimum over I equal to 1 to n of gamma I hat. Now let us see the concept of geometric margin. So here is our two-dimensional space with positive and negative samples and a decision boundary denoted as W transpose X plus B equal to 0. So our decision boundary corresponds to the parameters W and B. Here we are having the vector W. Note that this W is orthogonal or at 90 degrees to the separating hyperplane or the decision boundary. So vector W is normal to the hyperplane. Now consider one data point shown here as A. This data point represents the input xi of some training example with the label yi equal to 1. Now we have drawn one perpendicular from this data point A to our decision boundary, and this perpendicular meets our decision boundary at point B. So this line segment AB denotes the distance to the decision boundary from point A, and it is represented as gamma I. And we would like to find out now this gamma I. This data point A represents xi. So let us find first the point B. How do we represent this point B? Well, W divided by norm of W is a unit length vector pointing in the same direction as vector W. So point B is given as xi minus gamma I into W divided by norm of W. This point B lies on the decision boundary, and all the points those lie on decision boundary must satisfy the equation W transpose X plus B equal to 0. Now by substituting point B at the place of vector x, we can write W transpose into xi minus gamma I W divided by norm of W plus B is equal to 0. By solving this expression for gamma I, we get gamma I is equal to W transpose xi plus B divided by norm of W. So that is equal to W divided by norm of W whole transpose into xi plus B divided by norm of W. So this expression is meant for training example A, meaning the distance of data point A from decision boundary is denoted as gamma I, and that is given as W divided by norm of W whole transpose into xi plus B divided by norm of W. As I mentioned, this was worked out for the case of a positive training example, that is A, shown in this figure. So in general, if we would like to compute geometric margin of WB with respect to any arbitrary data point xi, yi, simply we can multiply the above term by yi. So in general, gamma I is given as yi multiplied by W divided by norm of W whole transpose into xi plus B divided by norm of W. If norm of vector W is 1, then functional margin is equal to geometric margin. Also, the geometric margin is invariant to rescaling of the parameters. That is, if we replace W with 2W and B with 2 times B, then the geometric margin remains same or it does not change. Due to this, we can impose an arbitrary scaling constraint on W without changing anything important. This will help us in dealing with optimization. We are going to talk about this later. So we computed geometric margin for a single data point. In fact, our training data set contains n number of data points. So let us assume that we are having a training data set S that includes n number of data points such as xi, yi. Then the geometric margin of WB with respect to this training set S is defined as the smallest of the geometric margins of the individual training examples. So for every training sample in the training data set, we are supposed to compute geometric margin gamma I. And out of these n gamma I values, we will find out the minimum value, and that denotes the geometric margin for the entire training data set S. In this session, we covered two important concepts: functional margin and geometric margin. These are being used in optimization. So with this, let us conclude today's session, and we'll see you next time with the concept of the optimal margin classifier and the optimization and duality problem. Thank you.